problem 3 on practice exam 3 of chapter 1 in the book Problem Solving Guide for Differential and Integral Calculus. This problem involves the ideal gas law, PV is equal to nRT, for isothermal processes and no change in the amount of gas that's in the container. PV is some constant. When the gas is at a pressure of 100,000 newtons per square meter and contained within 100 liters, the constant is 10,000 joules, a unit of energy. This relationship is shown in the plot here. For high volume, the pressure is low. For high pressure, the volume is low. It's an inverse relationship. So part A asks, with the tangent line, estimate the change in volume of the gas when the pressure is increased by 1,000 from 60 to 61,000. So we're going right here, we're going to go over 1,000 from 60 to 61. A small change. Let's locate the point and let's draw a tangent line. And we can get the slope of that tangent line to see how the pressure changes with volume and how the volume changes with pressure in this region. Slope is the rise over the run. The rise, we're going to have to eyeball that. It looks like 0.33, that's my guess. Maybe a little bit higher, I don't know. If you look at the run, that looks like that's 120,000 newtons per square meter, so we can get the slope. It's negative, the line's going downward, minus 2.75 times 10 to the minus 6 cubic meters every newton per square meter. Now we can calculate the change in the volume because we know the change in pressure and we know how they change. We know the ratio of their changes in this region. So the slope is the rise over the run, and we're running 1,000 newtons per square meter away from 60,000. We can calculate delta V by multiplying both sides by 1,000 newtons per square meter. We do that and we get the slope, the change in volume, minus 0.00275 cubic meters. And remember that we estimated this slope. We estimated that rise, so maybe we shouldn't include 3 significant digits here. We're not sure, but we can check with the normal equation. The normal equation relates the pressure and the volume. The difference equation relates their differences. The normal equation is PV is equal to 10,000. We can plug in a pressure of 60,000 and calculate V. So that's what V is. Now we can plug in a pressure of 61,000 and calculate the volume there. It's a little bit less. We can get the volume difference by subtracting them. And we get minus 0.00274 cubic meters, which is remarkably close to what we got using our estimate of the tangent line. So now we can do part C. What's the difference equation? This is a little bit of a challenge. We have P times V is 10,000. What's the difference equation? So we're going to change P, and V is going to have to change because their product always has to be 10,000. So this is 1 point, PV is 10,000. We move a little bit away, and we get P plus delta P, and V is going to change by delta V. So this is our new point, a different pressure and a different volume. And the product has to be 10,000. So now we can multiply this out. This PV is 10,000. We know that. PV is 10,000. So we can subtract this from both sides. So subtracting PV from both sides, which is 10,000, will give you a 0 over here, and it just gives these 3 terms on the left-hand side. So we know the total is 0, which means as one goes up, the other one has to go down. So we can factor out the delta V. There's a delta V in the first and third term. And we can do some algebra and solve for delta V. And there's the answer. It's not in the form that most people would like, but that's the right answer. That's the way the volume changes with pressure. Now let's tackle part D. So we're going to use the difference equation to get the answer, to get the change in volume for that change in pressure. So here's the difference equation, and what I talked about previously was you should probably have this in terms of P. Right? We're at a P and we want to change the P. That's what we know. We don't want to have to calculate V. So we're going to get V in terms of P, and we can get that with the normal equation. So V is 10,000 joules over P. So we're just going to substitute this expression in, so we only have P's and delta P's in our equation. So that's what it looks like. So it's 10,000 joules delta P divided by P squared plus P delta P, and the whole thing's negative. So P is 60,000 and delta P is 1,000, plus 1,000. So there's the 10,000 joules, there's the delta P, there's the P squared, there's the P delta P. And we solve this for delta V, and we get minus 0.00273 cubic meters, and we're very happy with that. So now we're going to zoom in to see if we can check this change, just to make sure we know what we're doing. This little tiny square, there's this little tiny square right here that goes from 60 to 61, and we're going to look at this pressure, the volume drop on this side, to see if it makes sense. And as you might expect, the line is going to look straight because the pressure change is so small. There it is. So there's 60,000, there's 61,000. We're looking at a very small section of the previous graph. So this point is 60,000 on the horizontal axis, 0.1666666 all the way out on the y-axis. And this is 61,000 on the x-axis and 0.16393 cubic meters. And we can subtract them and get the difference, and it's what we thought. We're not surprised because we know what we're doing, right? Of course.